Good afternoon, everyone, and welcome to today's SANCOLD YPF webinar. My name is Ashley Kutsia, and I'm the chair of the SANCOLD Young Persons Forum. Thank you all for taking the time to join us for what promises to be a highly informative and technically relevant session. Today's webinar is titled Adoption of National Flood Studies Program Publications for Design Flood Estimates. Design flood estimates forms a critical component of dam safety, water resources planning, and hydraulic infrastructure design. The Flood Studies Program, or NFSP, represents one of the most significant recent advancements in flood hydrology practice in South Africa, and many of us are currently grappling with how best to implement and apply these new methodologies in practice. We are therefore privileged to have colleagues from the Department of Water and Sanitation joining us today to share insights into the adoption and practical application of NFSP publications for design flood estimation. Before we begin, I would like to run through some housekeeping items. Please note that the mics and cameras have been disabled for the session to ensure a smooth running of the webinar. If you have any questions during the presentation, please submit them in the chat function at any time. We will address as many questions as possible during the question and answer session at the end. You'll also be given an opportunity to raise your hand if you would like to ask directly. Please note that today's session is being recorded and the recording will be shared on the SANCOLD YPF LinkedIn page a few days after the webinar. And we encourage everyone to actively participate throughout the chat during the question and answer session. It is now my pleasure to introduce our speakers. Firstly, we have Mr. Peter Rademeyer, a scientific manager at the Department of Water and Sanitation. Peter has more than 30 years of experience in flood hydrology, specializing in flood frequency analysis, dam safety investigations, and flood operations. He has led or reviewed flood studies for more than 260 dams, most of which are classified as high consequence dams, and has played a significant role in the National Flood Studies Program, contributing to the advancement of flood hydrology practice in South Africa. Joining Peter is Mr. Ernest Oakes, a scientific manager at the Department of Water and Sanitation, with over 14 years of experience in water resource science. Ernest's experience includes flood hydrology, water resources hydrology, hydraulic flood modeling, design flood estimation, dam safety surveillance, and flood risk assessments. He currently leads and oversees specialist projects related to dam design, dam safety, and flood risk management within the department. Our third speaker is Mr. Jermaine Nathaniel, a production scientist at the Department of Water and Sanitation. Jermaine holds degrees in hydrology and soil science from the University of KwaZulu-Natal and has over 10 years of experience within the department. His expertise include hydrological data monitoring and analysis, water resource management, flood hydrology, and dam safety applications, contributing to specialist hydrological investigations and assessments that support water resource planning and dam safety management. On behalf of the SANCOLD and the Young Persons Forum, I would like to thank Peter, Ernest, and Jermaine for taking the time to share their knowledge and experience with us today. Without further ado, I will hand over to Peter and the team.
Thank you, Ashley. Ernest, if you can share. Thank you. Thank you, Ashley, on behalf of me and Ernest and Jermaine. Thank you for this opportunity and thanks to SANCOLD. We appreciate this. We're going to have this information session regarding the adoption of the NFSP publications for the design flood estimation by the DWS. Thanks, Ernest. Okay, so what I'm going to do is I'll just do the first slide just as an introduction, and then I will hand over to Ernest and Jermaine to do the second and third parts of this presentation. Okay, so I think we're all familiar with the fact that of the importance of design flood estimation. Dams are critical water resource infrastructure, and their design and ongoing maintenance is integral for water security and public safety. Design flood estimation is a critical component of dam design and dam safety evaluations. So in the DWS, flood frequency analyses are required for these purposes by internal clients. Our internal clients basically are primary clients are dam safety surveillance and then dam design. So it's important that ongoing integration of novel research is incorporated into the DFE to ensure that relevant information and techniques for estimating design floods are adopted. That is one thing that we all agree on in the DWS working in the flood hydrology space, is that we make sure that the research that's being done by the NFSP is incorporated into our work. There's some really great methodologies and publications that came out of the NFSP, and we are trying to make it priority to incorporate all these publications and methodologies into our daily work. So this presentation will present the way in which research emanating from the NFSP and other relevant research and products have been adopted by the DWS for its DFE-related projects. Thank you, and now I'll hand over to Ernest. Thanks, Ernest.
Thank you very much, Peter. Good day, everyone, and thanks actually for the opportunity. So just moving on to some of the important considerations for design flood estimation. I'm sure that a number of you who have worked in the space are aware of the fact that one of the critical starting points is basically assessing and estimating your catchment characteristics. So there are various data sources that can be used to do that. But before we get into that, it's just important to note that catchment characteristics are important because, for one, it kind of goes without saying, you basically use that to estimate the receiving area, so the catchment that you're basically working on. And then the catchment characteristics basically also inform aspects of the analysis, such as how responsive the catchment is to design rainfall, as well as how long the critical storm duration will basically last. So in the case of catchment characteristics and catchment response, we all know that various methods have got various ways of quantifying the catchment response to rainfall. One such example is basically the rational method C coefficient, which is simply a number that ranges between 0 and 1, which basically is a fraction of how much of the design rainfall will basically be converted to storm flow. And in the case of the SCS method, which is another commonly applied method, it uses basically a curve number, which is used to quantify the amount of moisture in the soil before a design flood event. Now, when we come to the discussion about critical storm duration, so that's a term that we have started using at the DWS, considering the fact that we're no longer just using time of concentration and isolation. We also use the time to peak, which is something that I'll be discussing as we go through the presentation. But that's basically now, how long does the design storm last that will basically cause the flood in question to happen, which is quite important when it comes to the design, or I should rather say the frequency, depth, and duration components of the design storm, which basically needs to be considered. So when it comes to catchment response, there are several factors governing the catchment response, such as your catchment land cover, catchment soil, and soil characteristics, specifically permeability. And there are various data sets that one can basically use to estimate that with justification. So it's not just limited to what we have over here, but what we have been using at the DWS as much as possible is the most recent land cover data set, which is freely available from the Department of Environmental Affairs. We also use digital elevation models to estimate catchment characteristics such as the catchment boundary, as well as aspects such as catchment slope. And there are various digital elevation models that one can use to accomplish that. Some of the ones that we actually specifically use are the SRTM the merit, and then the Chief Directorate National Geospatial Information, CDNGI DIMS. There is a bit of a preference from time to time to use CDNGI DIMS because they can be of quite good quality, but that should still be verified, for the project that you're basically working on. But if we don't have that available from the CDNGI, one can lean on the SRTM or even the merit DIMS, depending on what's available for the project in question. But one is not limited to this. One can even make their own digital elevation models using contour information, which is something that we would tend to do, especially if we're working in very small catchments, considering the fact that the resolution of these data sets is at best 25 meters. So that's just something just to take note of in terms of the analysis and digital elevation models. And then fairly recently, we have also started using the terrain units that were developed by Shooter and colleagues at UKZN, also freely available as far as I can understand, and can be requested from them. So that's basically how we do our best to ensure that we are using up-to-date data sets for the analyses that we are basically undertaking. When it comes to critical storm duration, I indicated earlier on that we no longer to TC as something that we measure. It's actually now a more sort of like broad and general all-encompassing term known as a critical storm duration, which is quantified using your time of concentration or your time to peak, and which can be estimated using various catchment characteristics and data sets. Some of them, which we will discuss in the subsequent slides, include aspects such as land cover, characteristics which can be estimated from DIMS, and then certain methods may also require MAP, which could be estimated from data sets such as your WR 2012, your design rainfall utility, or DWS catchment rainfall approaches that have been extensively discussed at the Stellenbosch Flood Hydrology course at the University of Stellenbosch. So when it comes to the time of concentration, this is an approach that is frequently used both locally and abroad to estimate your critical storm duration. It does produce some reasonable results, but there are concerns about the fact that it was developed in the United States in very small catchments. So not even locally developed, but developed in a completely different country on quite small catchments. And ourselves, as well as other people, do tend to use this time of concentration equation in fairly large catchments as well. It does produce reasonable results, but there is just a bit of a concern about the fact that it is actually used outside of its intended purpose. But unfortunately, we don't actually have too much to go on, with the exception of the time to peak approach, which I will be discussing as we go through the presentation. So this is one of the publications that actually came out of some work done by Professor Hedeke at the CUT, as well as his collaboration with other colleagues. So it is the other approach that we basically use to estimate the critical storm duration. It requires various catchment characteristics such as the MAP, catchment area, and the average catchment slope. And the advantage of this approach is that it does actually, or I should say it was actually developed to estimate catchment response in medium to large catchments. So the time of concentration equation was actually developed more for small catchments, although it is actually used for large catchments. But the authors of the time to peak equation basically had in mind the need to estimate critical storm duration for medium to large catchments. And that is actually something that we have adopted for our projects where possible. So it's just important to note that the work that is being undertaken on this has been undertaken for various drainage regions in the country, such as the A and the X, and various others in KwaZulu-Natal, as well as the Western Cape and the Central Interior. And there is ongoing work to expand that into the remaining parts of the country. So one must just be aware of the fact that there are some limitations in the fact that the whole country hasn't been covered yet, but work is being done to bridge the gap there. But like all methods and all data sets, it's just important to apply due diligence when undertaking a flood frequency analysis or design flood estimation, and understand what you have available for you to undertake your project and to work within those limits. Now, when it comes to catchment design rainfall, so once you've basically estimated your critical storm duration, you basically know how long it's going to rain for. So you've basically, how can I say, answered the question, or one of the input variables required for the depth, duration, frequency requirements for your design rainfall. We at the DWS use various ways of getting onto the depth of the rainfall that we basically need to account for. So the critical storm duration is one thing, the return period is something else, but then estimating the depth is basically undertaken either using one of three DWS approaches, namely the DCR, or the daily catchment rainfall, or the maximum station rainfall approach, which basically consists of two approaches where we either apply catchment statistics or station statistics. And then we also apply the design rainfall utility approach as well. So we will try apply all sorts of different approaches to estimate the design rainfall depths for our projects, considering the fact that design rainfall is actually one of the most important input parameters for estimating a flood peak or a flood height graph for a particular project. Something else that we have also given consideration to that we incorporate into our reports now is climate change. One of the approaches, or I should say one of the reports that we often use, is basically the work that was undertaken by Shuter and colleagues at the University of KwaZulu-Natal. So what we will do is we'll see for a particular area what the report suggests in terms of the required adjustments for design rainfall and storm flow volumes. And then taking that into consideration, we'll basically look at the approaches that we have, consider their limitations as well as their advantages in terms of how they estimate catchment design rainfall. And then we'll basically assess the results and see what can be done with the findings to be able to account for climate change within reason. So what we will sometimes do is use one approach over another because it may meet the climate change requirements. So it's not just a straightforward adjustment of a certain percentage up or down to account for climate change. There's a detailed assessment of the outputs from certain catchment rainfall estimation approaches, which is then used to basically lead to the conclusion that a certain type of magnitude should be adopted for a particular project. Something else that we've also started using is the probable maximum precipitation and the work, or that comes from the work done by Johnson and Smithers in 2020. So an extensive amount of work went into that. It's important that we do consider using it in our projects. It's just important to note that the estimation of the PMP is something that one can establish with great confidence considering the work that was done. But what is still a gray area is estimating the probable maximum flood. So one basically needs to convert a precipitation into a flood value. There are deterministic methods that can be used to undertake that, such as your rational or your SCS approaches. It's just important to note that the literature that was published and that documents the way in which one can do that states that one should actually apply this with due caution, because when applying these deterministic methods or other such methods to convert a PMP into a PMF, you need to make adjustments to the method to account for catchment characteristics and the storm flow response when that probable maximum precipitation basically takes place. So there are limitations that one needs to be aware of, but there are ways to estimate the PMF. But my suggestion would basically be just to echo the sentiments of the literature. One should do it with due caution applied and just understand the limitations of the approach to estimate the probable maximum flood. I'd like to hand over to my colleague Jermaine, who will basically take us through the remainder of the presentation. Thanks very much, JJ. On to you.
Good afternoon, everyone. The previous sections focused on the earlier stages of the design flood estimation process, specifically the selection and assessment of hydrological input data. And these are utilized for us to apply commonly known flood estimation methods, both in the deterministic and empirical method categories, which are listed on the slide in front of you. These include rational, SES, SA, DRH, SUH, Kappa, as well as the MIPI 67 and 71 approaches. And these approaches are particularly important in the absence of stream flow data, and we need to apply them and make judgments with due diligence in the absence of at-site information in the form of an annual maximum series. Thank you. I'll now focus on the statistical methodologies currently utilized by the Department of Water and Sanitation, particularly recent developments in flood frequency analysis and the methodologies applied in evaluating extreme hydrological events for final design flood determination. The Department of Water and Sanitation has incorporated the Z-set plotting position into our statistical flood frequency analyses as an updated alternative to more traditional plotting position methods such as Cunane, Weibull, and other approaches that are typically used to assign exceedance probabilities to observed flood peaks. The benefit of this updated methodology is that it addresses some of the known limitations that conventional plotting positions have when working with flood data sets, particularly where extreme events or irregular observations are present. In practical application, several improvements have been observed. Firstly, the method eliminates the tendency for flood peaks of very similar magnitudes to be assigned noticeably different exceedance probabilities. Secondly, it provides a more realistic representation of outlier events, which is especially important when analyzing extreme floods. In addition, the plotting position itself produces a much smoother probability trend that more closely resembles the behavior of a statistical distribution. And importantly, the assigned probabilities remain more consistent across data sets with different record lengths. Overall, this gives us a more reliable statistical foundation before moving into distribution fitting and design flood estimation. Next, please. The development of the Z-set plotting position established the foundation for a new distribution, namely the IPSA, or Improved Probability Model, South Africa. From its application, several important observations have emerged. Firstly, the IPSA methodology appears more likely to impose a practical upper bound when compared with conventional approaches such as GV and LP3, reducing the tendency for unrealistic extrapolation at very low exceedance probabilities. Secondly, the distribution has shown far greater stability and consistency in the estimation of flood quantiles across a wide range of analyses. Finally, because the methodology better incorporates the influence of outliers directly within the statistical process, it has been proven a valuable addition to our decision-making tool for hydrologists and engineers, particularly when we are assessing extreme flood events where confidence in the analysis becomes most critical. Next slide, please. Extreme floods, RMF revision and adoption into DWS practice. For many years, the methodology developed by COVAX for estimating the regional maximum flood, or RMF, has been used as the standard basis for determining the safety evaluation flood for category 1 to 3 dams, particularly prior to conducting a more detailed site-specific analysis. However, an important limitation identified within the original methodology is that all regional approaches apply common regional factors across broad geographic areas, which means the site-specific hydrological behavior of an individual catchment may not always be adequately represented. To improve this process, more recent work by Duplessis and Masule revised the original RMF methodology and updated the regional framework for South Africa. Based on these developments, the Department of Water and Sanitation has now adopted these revised findings within its detailed design flood estimation studies. Thank you. Within the Department of Water and Sanitation, numerous detailed site-specific flood analyses have shown that the estimated 10,000-year flood event tends to correlate very closely with the RMF. This relationship has become an important observation in our current approach to evaluating the extreme flood magnitudes when assessing dam safety. Based on this, the department determines what is referred to as a site maximum flood, or SMF, by considering the magnitude of the 10,000-year flood together with additional factors such as climate change, extreme flood observation from nearby sites or other historically significant events, and comparisons with the probable maximum flood. From this assessment, the safety evaluation flood is then determined by adjusting the K value of the SMF according to the relationship shown in the equation on this slide, where an additional safety factor is incorporated to ensure a sufficiently conservative estimate for dam safety evaluation. All of the methodologies that have been discussed in this presentation all work together to bring us to this point where we are able to provide our dam safety clients with an appropriate RMF, SMF, and SEF, as well as other important design flood estimations and hydrographs that can be used later on in the broader dam safety inspections. Next slide, please. Much of what we do in DWS has been taken from many years of research done in the country from various institutes, universities, and hydrological units. And these form the basis upon which much of the updates we've worked with have been incorporated into our analyses. So for ease of reference, we provided in the last 4 slides all of the publications and the references, and these can easily be found online so that you can look at them yourself and get more information on these methodologies. Thank you for your time, everyone. I'll hand you over back to Ashley for the remainder of this session.
All right. Thank you very much to our presenters for an excellent and thought-provoking session. We'll now move into the question and answer portion of the webinar. If you have any questions, you're welcome to either type it in the chat or use the raise your hand function in Teams. If you raise your hand, I will invite you to unmute and ask your question. We'll do as many questions as we can for the allotted time. I don't see any questions in the chat at this stage, so if you want to raise your hand, please do so. Okay, we have a raised hand. Please unmute yourself and ask your question.
Thanks, Ashley. Thanks, nice presentation from Peter and Ernest and Jermaine as well. Thanks, guys. I just had a quick question. Obviously, department's very used to working with these dams and large catchments. For us, from a roads perspective, obviously designing bridges and culverts, catchments vary significantly in terms of size as well. When it comes to point precipitation, how does the department normally handle your rainfall depth, your design rainfall depth on a large catchment? There's things like this in polygon and things, but if you had to use something like the design rainfall utility, and where you'd have quite a large variation of rainfall over a large catchment, how would you normally approach those type of applications?
I'll go ahead and answer that, Ashley. So thanks very much for the question, Shahil. What we normally do is, I forgot to mention during the presentation that we also apply the newly developed area reduction factors by Dr. Peterson from the Central University of Technology. So what we would normally do is apply the different methods in terms of the Thiessen polygons. So our DWS approaches actually require us to manually select rainfall stations spread throughout the catchment. We then extract rainfall information that we have available for it, or for them, I should rather say. We do a statistical analysis, but then we also apply Thiessen polygons to weight the rainfall stations as well, and apply area weighting factors to weight those stations values, so we can basically get a depth of catchment rainfall. But then, depending on the size of the catchment, the ARFs that were developed by Dr. Peterson at the Central University of Technology are actually applicable for 1-day durations and longer. But based on personal communication with Dr. Peterson, one can actually reduce the applicability of those ARFs down to about half a day, so 12 hours, if I remember correctly. So we will, when using the design rainfall utility and our so-called maximum station rainfall approaches, we will apply an ARF to the design rainfall depths, and then use those aerially distributed rainfall depths in our design flood calculations. When it comes to the daily catchment rainfall approach, we generally don't apply an ARF because we actually area weight the daily values prior to undertaking a statistical analysis. Now, in terms of very large catchments, we basically apply a very similar approach. So what generally happens is that some of the methods that one can basically use, such as your SUH or DRH approaches, are applicable up until maybe, say, 5, 10, or maybe 20,000 square kilometers. We actually still just apply those methods outside of their bounds as well. One could maybe make the argument that maybe one should sort of like start subdividing catchments and maybe apply or estimate catchment rainfall for the incremental catchments as well. But there's many ways of estimating design floods using the different methods. But in terms of how we estimate our catchment rainfall, that the approaches I've just discussed with the ARFs and the various approaches is how we would normally go about estimating our design catchment rainfall depths. I hope that satisfies your question.
Sure. Thank you so much. Yeah.
We have another question in the chat saying, hi, can the presenters please expand on their methods of determining design rainfall and where to find these sources? I know you spoke a lot about design rainfall now, but maybe just expand a bit on that.
Sure. So what we would normally do is we are fortunate that, for the whole country, we've got the daily rainfall utility. Sorry, my apologies, the design rainfall utility for estimating design rainfall off the cuff just by, extracting a point, I should say, grids for your catchment and basically then applying them over your catchment and estimating your design rainfall. What we also do is we frequently use the design rainfall utility as well, which basically gives which basically has patch data from about the mid-1850s all the way up until 1999. So we also use that data set, which is freely available to estimate our design rainfall. Unfortunately, for most of our projects, estimating, or I should say using rainfall values after 1999 is a bit of a challenge. I'm sure we're all aware of that. But I think if you have a long enough record, even if it ends in 1999, it should be fine, considering the fact that you're basically doing a frequency analysis on the rainfall values, and up-to-date rainfall data could probably be foregone in the event that it is not available. I hope that satisfies the question in the chat.
Okay, we have another raised hand. Hold on, you can unmute yourself and ask your question.
Hi, afternoon, everyone. Thanks so much for the presentation. Some interesting lessons so far. I've got two questions. The first one was, we've had some experience, or I've had some experience where using the Johnson and Smithers new PMPs rather than the HR 172 sort of curves, where the PMP is significantly different between those two. I'm curious to know if you guys have found similar things and what your approach was to sort of come to a conclusion as to what to use as a PMP. And then the second question is about the extreme floods, where, as I understand, you sort of calculate a new KSEF with your SMF plus a factor, and that factor takes into account the probable maximum flood. This seems quite different to sort of the SANCOLD guideline, where you have a SEF which is just applied by a factor using a RMF sort of ratio. How does this approach with the KSEF and KSMF compare to the sort of SANCOLD guidelines of doing a SEF calculation for dams?
Okay, so the calculation of the PMF, like Ernest said, is still, in my opinion, it still hangs in the air. So we will evaluate the PMP, and we will use the rational and SS methods to estimate the PMF. The problem with that is when you're working on big catchments, the rational and SAS methods were developed specifically for small catchments. So one must be careful of the values that you get there. And what we have seen is that most of the time, the PMF values are just overestimated. We do that just to check, just for, let's say, just for analytical purposes. The PMP values, so the precipitation values we found are more or less okay. So that's not the problem, but the PMF's the problem. So at this stage, we're doing it, but we focus more on the RMF. So just your second question was regarding the SEF and the RMF. So what we basically do, look, the RMF is based on observed flow data. So that's, in my opinion, that's very important because you've got something to work with. And so we will look at we will evaluate when we do a statistical analysis, when we have that data available to us. We've seen that, as Jermaine has said, that your 10,000 estimate in most cases are very similar to the RMF value. And that to us is a good guide in then reducing the SEF value. So we basically consider the RMF as a guide to, in the end, propose the SEF value. I hope that answers your question, Odon.
Yes, thank you. Yeah.
Okay, we have another question in the chat. It says, with regards to statistical methods, the DWS hydrology site only contains data for gauges river stations. How do we go about analyzing for ungauged stations? Also, are there freely available rainfall data collected by DWS or other institutions recommended by DWS specifically, because the rainfall data from Smithers software are fixed for the previously observed data? Lastly, there has been a publication for the determination of area reduction factors. Has this method been fully employed? And if so, are the GIS database example shape files available? The question is in the chat if you want to just look at the 3 sections.
Thank you, Ashley. Okay, I think I'm going to start with the last one. It's the quickest one. Yes, there are. Yes, so we have employed the new IRF factors into our work. We have done so, yes. There are GIS data sets available, shapefiles, that's available, yes. So we can supply it. That's not a problem because it's freely available. Okay, let me just check. The first one is regards to statistical methods, ungauged sites. Okay, so what we usually do is, say for instance, you doing an analysis on a catchment that's in close proximity to a gauged catchment. Then you can use the gauge catchment as a guide to do what we call a pseudo-statistical analysis. So we will run through all the methods. We will do a proper analysis at both sites. Then we will look at the gauge catchment to see how the statistical analysis perform in relation to the other methods. And then we can apply an adjustment factor to 1 or 2 of the methods in the ungauged catchment to actually then estimate flood peaks for the ungauged catchment. Rainfall data. Okay, so we've got, yeah, the rainfall data is problematic. That's a short answer. We do have extra data from 2012 up until 2022 that we actually bought from source. But what we found working through some of these data sets is that the data has basically not been verified. There's a lot of gaps in the data records. So one must be careful when working with these data sets. But the DWS, we are trying to negotiate with source. I know it's an issue, but let's see where we're going to go with this. But unfortunately, we have signed an agreement with Source that we in the DWS will not supply someone on the outside with the data. But I think a way to maybe get around that is to incorporate the data sets into WRC projects, something like that. I hope I'm answering those questions. I just want to check the lot. There's another one in the near future. Will there be a software of the current existing DFE Excel file? So we've got software that we have developed in-house in the DWS, especially for the statistical analyses. We've got a really good, solid statistical analysis Excel software that we can share. That's not a problem. We can do that. Okay, Ashley, maybe over to you again. Thank you.
Thank you. Yes, we have another raised hand. So you can unmute yourself and ask your question.
Hi, Peter, Vikas here. I want to come back to the dams world and RMFs and so forth, following on Odon's question. How's it, Odon? So just to check, for smaller catchments, you're talking specifically about large catchments, would you still propose that the RMF to SEF methods are better than a site-specific method to get to an SEF for for smaller catchments specifically? Let's say it's we don't recommend RMF methods at all if it's smaller than the 10 square kilometer catchment size, but let's say you're in your 20, 30, 50 type of range. That's my question one. And then on the same topic, I heard a rumor that, and I don't know if it's only related to the updated RMF methodology, that it's not proposed to use the old methods of scaling to, say, a Q100 and Q50 from RMF, even for dam methods. That's quite popular for your in your dam world, for at least for first estimates and so on. But I heard a rumor that Prof. Du Plessis actually said that should rather not be done. So I don't know if you have a comment on that as well. So 2 questions. Thanks, Peter, and move on.
Okay, thanks, Vikas, for the questions. Okay, your first question regarding the RMF on small catchments. Yes, you need to be a site-specific. We always do a site-specific analysis. If we, on small catchments, large catchments, we do a site-specific analysis. So I think it's very important, especially on your small catchments, to do a proper site-specific analysis. We know that in your smaller catchments that the RMF can be problematic, and that's just because we don't have enough data to actually confirm the values in the transition zone. So site-specific analysis is good. You can use the RMF. You can use it as a guide, but do a site-specific analysis and look at, I would say, look at your, observed events in the region, maybe in close proximity to actually check that. Your second question, because what was that second question?
Sorry, Peter. It was related to scaling of the RMF to, say, for example, a Q100 or a Q200. So that's quite
yes.
in the dam world. Yeah, but like I said, I heard a rumor. Colleagues tell another colleague, that's rather not proposed anymore. And I don't know if it's related to the new RMF method, or if it's just now considered not good practice at all.
Yeah, we don't actually use that. We haven't used that since the TR137. I know there's those options to check the 50, 100, and 200 here. We don't use it. We've never used it. In short, we did check that, and we just came to the conclusion it was just totally overestimated. So we never use it. And I agree with Prof. Du Plessis. We don't use that at all. We use the new RMF methodology.
Thank you.
Okay, we have another question in the chat saying, how critical is DTM size in the estimations? Is the 30 by 30 meter usually obtained from USGS acceptable?
Hi, Ashley, I'll take on that question. So from our experience, especially working in larger catchments, a 30 by 30 meter resolution DEM from the USGS is fine. In actual fact, we frequently use those. And it's just important that when you use a digital elevation model, one should also just hydrologically correct it. So there are tools in QGIS and ARC, just Pro and ArcMap to hydrologically correct a DEM before you use it. So I must say there isn't a scientific approach that we take where we say, no, for a certain catchment size, we shouldn't use a certain DEM. We would sort of like, how can I explain, maybe perhaps get an idea as to whether the catchment boundary looks realistic, having used maybe a 30 by 30 meter DEM. If it doesn't look realistic and it looks like there's portions of the catchment which should have been included, we may consider just using a different data set compared to what we got with the 30 by 30 meter DEM. And if it performs better, then we'd actually rather go with that. So there is a bit of there's no hard and fast rule. It's basically we look at the data that we have, look at the scenario that we're faced with, and then we proceed with justification to the best of our ability. This kind of like leads me on to the next question from Ms. Cox about the rainfall and the various approaches. So it's not a fixed recipe that we would follow. We would estimate the catchment rainfall for every single project using multiple approaches. Consider uncertainties such as climate change, some of the data limitations, and how spread out the stations may be, or how dense the network may be, and then based on that, with sufficient motivation, propose a certain type of design rainfall depth from the various approaches that we basically use. So I can't give you a solid recipe that we follow. It's basically constantly applying scientific judgment and professional judgment, and then estimating our design floods in that particular way, and design rainfall in that particular way as well. Thanks, Ashley.
Thank you. We have another question. When deciding between your multiple approaches to estimate catchment rainfall, how do you decide which to use? Is it sufficient to make use of the design utility software as long as there are enough years of data available? Also, when back calculating K from the Q 0.01%, do we make use of the folder Francois Rudier formula, and then with a calculated K, use the 2023 or 1988 formula to work out the SMF?
Okay, so in terms of the first part of the question, I tried to address it when I was speaking earlier on. So again, it's just basically a case by case where, even though we've got limited data, we just try to do the best that we can with the information and the approaches that we have available. In terms of the back calculation of the K value, we have now started using the 2023 RMF approach. So what we would do is we would estimate. We basically have a series of K values estimated for various K values for the particular site that we're working on. And we basically use that information along with the equations to back calculate the K value for the Q10,000 value that we would have estimated for a particular site. So we have less and less been using the 1988 approach, although we still do include it in our investigations, but we tend to use more of the 2023 approach as well. And we tend to focus on that and basically use those approaches now to estimate the K value for the 10,000 value, and then basically use that to propose an SEF. Peter, I don't know if you want to weigh in on that as well, but I think I hope that pretty much covers it.
Yeah, I think it's one. Thanks, Ernest.
Thanks, Ashley. Over to you.
Yeah, we have Shahil again raising his hand. You can unmute yourself.
Thanks again. Just another one, just a quick one from my side. Selection of catchment methods. I think, Peter, you covered it in terms of this, regardless of catchment size, there's always a site-specific analysis that's done, which I think it's good best practice. Currently, there's obviously a lot, previously in guidelines and stuff, there's been a lot of guidance provided to designers and practitioners based on catchment size in terms of which methods to apply. And with the rational method, I know that in terms of DWS, it is applied to large catchments. So most guidelines normally point to 15 to 20 kilometers square. But obviously, with caution of having experience and all the data sets that were presented earlier today, making use of as much information as possible when determining like a coefficient of runoff and catchment characteristics. What's your opinion on applying rational method on the large catchments, and are there any other sources apart from land cover, the soils map, and the DEMS that are used for slopes and things like that? Thanks.
Okay, so we do when we do a analysis on a catchment, it can be small, it can be medium, it can be large. We actually utilize all the methods, and the one reason why we do it is we need to give feedback to the guys at universities doing research, etc. They need to have that information because they will then do the research and look at the results, and from their side also give feedback. So we've done it on let's take for instance the rational and the SES. Prof. Smithers has asked us a few years ago to actually try and use the SES on bigger catchments. Now, you know that the SES was developed for small catchments, but we actually do use it on bigger catchments. So the catchment will be divided into sub-catchments so that the SES method can actually adequately accommodate those different catchments in the bigger catchment. And we've also done that with the rational method. We've utilized the rational method on big catchments, and to our surprise, actually, a lot of the analysis that we've done, both the SES and the rational, has given us good results that's comparable with your empirical methods. That was designed for or developed for your medium to larger catchments. And even with a statistical analysis, we found that on some catchments, they performed quite well. And yes, we try to utilize all the information available. All the land cover information. We actually have land cover information from 2016, 18, 20. So we're trying to utilize all these kind of data sets in the analyses. And yeah, but it was interesting, from what we saw that even in the bigger catchments that the rational and SES did not, surprisingly, it was actually not bad. It was good. But let me say, it's not in all the catchments, okay? Not in all the catchments. In some catchments, we saw that these methods totally most of the time underestimated or even overestimated, but there were some surprises there. But I think what we're trying to do is we're building up a database. We have an Access database that we've started. And what we're doing, so all the analysis that we're doing, we're putting all the results into this database. So we're using all the catchment characteristics, the different rainfall approaches that we use as input for these methods, and then the final results. We're putting everything into a database. And we're doing that specifically so that the guys at universities can do the research, take these results further, so that in the end, I think what we want to see is from the research is then publications that will show us in what specific areas in the country, how specific methods perform in the country. So maybe you'll have, like, for instance, your MIPI and your Kappa method will perform really well in specific parts of the country. So that's what we want to see, so that all of us can actually use that, and specifically the practitioners going forward, use those results to see, use it as a guideline going forward in the analysis that they're going to do. Thank you. I hope that answers your question.
Actually, could I please maybe just come in? I
Yes,
just want
please.
just to add on to what Peter was saying. It comes back because Peter would mention that we've seen that the SCS method and the rational method do perform well in some catchments. It's just important to note that it also just comes down to how you interpret your data set, so your land cover and your soil. The land cover being a bit more complicated because if you download the land cover data set from from a source such as the Department of Environmental Affairs, one has got to now apply their own judgment as to how you basically would classify that according to, for example, the rational method classification or the SCS method classification or some other methods approach of classification as well. So one must just keep that in mind. And also, it also depends on the rainfall that you're using. So we mentioned earlier on that we apply various different approaches to estimate catchment rainfall. We have found that if you apply a certain method's rainfall to a certain method, or a certain approach's rainfall to a certain method, you may find then that the method actually performs quite well to the stats. So, one shouldn't just assume that the method performs well. It's also just some background work and background thought that has to go into the inputs that you're providing to the method as well. So, one must just keep that in mind. Thanks, Ashley. And I think CJJ may want to make a contribution as well. Thank you.
Yes, go ahead.
Yes, thank you, Ernest. I actually just wanted to add on to what Ernest had said, particularly with the SCS method. I think in the past, when we'd make use of the model, we would use a lot of the built-in land cover classes and so on for the model itself to calculate the curve numbers. And in recent years, Ernest has worked on us calculating the curve numbers outside of the software. And you'll see when you use the SCS, you have the option of either using the classification system built within the software, or to put in your own curve numbers that you calculate based on your site information. And so, like you mentioned, we've got the Department of Environmental Affairs latest land cover data sets, as well as the UKZN terrain units that now replace the older SCS soils. And what we do is a bit of a more detailed analysis of the land cover and the soils outside of the software to get our curve numbers. And what I've noticed, at least I'll say personally, is that from my analyses in the past where I would use the SCS compared to the approach we use now, I see the SCS method performing a lot better than previously, and often supporting rational and the statistical results much better than it did in the past with a more broad way of using the approach. And so I think calculating curve numbers in a wise manner using the land cover and soils best information we have, along with choosing the appropriate lag equation. I think it's the soils, the land cover, the rainfall, and your choice of lag equation that actually makes a big difference in how your SCS final results compares to perhaps your stats if it's available. It makes a big difference. And in what I've at least noticed personally is that despite the 30 kilometer square suggestion of using the model for that size limitation, I found that when we break up the catchments and work with it, as I've mentioned, with our own curve numbers, correct rainfall, and correct lag equations, often the SCS performs much better. I wouldn't say now it completely supports the statistics in all scenarios, but I've noticed that change. And so I think maybe that's something to take note of, and perhaps maybe in the way we approach the rational as well. I think the way we look at the rational land cover and soils information, I think the method, despite the so-called catchment size limit, the method can perform quite well when you look at those land cover, soils, and rainfall information in a more detailed manner. Thank you.
Thank you, colleagues. I don't see any further questions in the chat. We have suggested going to the guide for flood frequency estimates method on the DWS website. I've included those links for you so that it's easy for you to find. Sometimes the homepage can be difficult to navigate. Okay, while I've been talking, we've got another question. Is the STF method still used widely for flood estimation? We have found both under and overestimation when comparing with the rational method, ARM3, on medium to large catchments. It's in the chat.
Thank you, Ashley. No, we actually are not using the STF method. We did use it at one stage. We did do some checks on it. I know we had an engineer that worked here that did some evaluations on it, and we actually found it in most cases to overestimate. So at this stage, we're not using it. Maybe in future, if it's been revised, maybe we'll look at it again. But this stage, no. Thanks, Ashley.